In this video we talk about timing details of sequential circuit. So that means we will be understanding how to fix the frequency of a clock. What are the parameters which are going to influence it? So let's begin with two important parameters. One is propagation delay and setup time. Let's begin with propagation delay. Propagation delay is the length of the time. What it represents I will explain with example. Example, take this inverter and let's say your current input is 0. Alright. So, and the current output is 1 here. When this 0 is changed to 1, immediately this will not be changed to 1. Okay, take some time because the signal has to propagate through this. Alright. So, the duration 10 nanosecond is required for the propagation. Then after 10 nanosecond, this would become 0, and as long as this is 1, then this output will be 0. So the change is permanent after 10 nanosecond. So that is a propagation delay. That's it. Now let's talk about setup time. Setup time is a duration of time before the clock edge, here rising edge, where your input should be stable. Just remember it. Alright. Example, if it is 2 nanosecond, at least for 2 nanosecond of time before the clock edge, your input should be stable. It should not fluctuate. Alright. Now with the details what we have learned, we try to understand how to fix the clock frequency. Alright, this is your clock. Alright, so this is the first trigger, this is the second trigger, this is the third trigger, and so on. Now I would like to know what is the maximum time period we can have here so that there will not be any problem. Alright, okay, what are the problems we actually face? We try to understand. This is the sequential circuit, especially synchronous, correct? Okay, when we give clock, so this input, I am worried about this input D. So that is actually indirectly coming from this Q, correct? So that's why you have to know the relationship between this Q and D. Let me define what is Q. Okay, there are many Qs. So Q1 means the output which we get from this flip-flop, alright, after first clock cycle, okay, after first trigger, that is Q1. Similarly, Q2 is after second clock cycle output. Similarly, we have Q3 and you have Q4 and so on. Now let me elaborate. This is Q3, let's say this is Q4. Okay. At t equal to 0, let's say first trigger of the clock happens. Alright. When are you going to get this output Q1? Because this flip-flop has 10 nanosecond delay. So after 10 nanosecond time, you are going to get the first output Q1. Okay. Q1 is stable after 10 nanosecond. Same way. So for example, for easy understanding, I'm assuming that t value at this point, that means second trigger you are giving at 70th nanosecond. Okay, so at 70 nanoseconds, if you give the trigger, so plus 10, that means at 80th nanosecond you are going to get Q2. Same way Q3, Q4 can be imagined. Now let me introduce you the another input, that is D. So this is input for the second flip-flop. Okay, so this input we are going to give at first clock cycle, that means after first trigger, after second trigger, or exactly at second trigger, or exactly at third trigger, and exactly at fourth trigger, and so on. Okay, so D1, D2, D3, D4 are such values. What is the connection between this Q1 and D1 and Q2 and D2 and so on, or Q and D? See, can we give this Q1 directly to D1? Can we expect Q1 to be given to D1? No, because this D1 is nothing but input which is given to the flip-flop at t equal to 0, exactly at t equal to 0. But at that time Q1 is not available. It is available after 10 nanosecond. But after that also it has to go through this propagation, like this gate, correct? That takes 5 more nanosecond. That's why it cannot be available. Then why it is designed, like why it is connected here? So then easily you can understand that if you use common sense. So Q1 is specially used for D2, correct? Similarly, Q2 is used for D3, Q3 is used for D4, Q4 is used for D5. That point you should understand. It is very important for any sequential circuit. Now let me ask you one question here. This is your clock, one typical clock, alright? This is a clock period. This is your first trigger and this is your second trigger. Just focus on D2. So that input for D at this moment is actually coming from this Q, correct? for that first Q1 has to be prepared, and that should go through this inverter. Then after that, that should be connected to D. Alright. Okay. Now if you start noticing from here, at the first clock cycle that Q is not available. Alright. So when it is going to be available? After 10 nanosecond. Now after that, so that will go through this inverter that is having a delay of 5 nanosecond. Alright. So after that, input is ready. That means after 15 nanoseconds, input is ready for D2. But the setup time is 2 nanosecond. That means what? Though the input is available, it should be stable for at least 2 nanosecond. That means, 15 plus 2 nanosecond. At least 17 nanosecond time is required to take the input. Correct? So, from now onwards, whenever you are fixing the clock period, so you have to take care of all these parameters, right? The propagation delay of the flip-flop and this propagation delay of the combinational circuits and setup time. Okay. So your clock, clock period, let's say T, that should be either greater than or equal to this all 10 plus 5 plus 2. That means T should be greater than or equal to 17 nanosecond in this problem. Alright. Let's solve this problem, which is asked in 1991 paper. Find the maximum clock frequency at which the counter in the figure below can be operated. Assume that the propagation delay through each flip-flop is 10 nanosecond here. 10 and 10 and 10. And AND gate delay is 10 nanosecond. Here 10, here 10 and here 10. Assume that the setup time for the JK inputs of the flip-flop is negligible. There is no setup time. Alright. Now we have to find out the maximum clock frequency. Maximum clock frequency means minimum clock period time. Correct? Minimum clock period. So let's fix it. Let's say this is the clock period. Alright. Okay. This point is the first triggering. This point is the second triggering point. And between this we have a clock period. Correct? Okay. So we have to fix this value. And example, let's say here to give input to J2, we need some sufficient time. That means we are taking input for J2 from Q1's output, correct? Okay. So when are you going to get Q1's output with respect to this point? From this point after 10 nanosecond, once this flip-flop works, correct? Once this flip-flop works, then after 10 nanosecond, this gives you output Q2 and Q1, and that Q1 will go through this AND gate, and that takes 10 more nanosecond. So after 20 nanosecond only, so you are able to get a proper input for J2, correct? So if this clock time is not 20 nanosecond, if it is only 10 nanosecond, then things are not going to work, correct? So that's why, so time period should be definitely greater than or equal to 20 nanosecond. But we have another path that also we have to see, because your J2 is connected through this path also, right? See this path. Alright. Okay. So with the same thing, if you calculate, Q0's output comes after 10 nanosecond from this triggering point, correct? Okay. So after 10 nanosecond you get this Q0 output, then that will go through this gate. Then after 10 nanosecond it will come out. Then again it will go through this gate. Then 10 more nanosecond, right? That means after 30 nanosecond, so this is going to come to J2. So maximum path, if you see the maximum path, and that time is 30 nanosecond, correct? Right. So if the question is about what is the maximum clock frequency at which the counter in the figure below can be operated, if we are only focusing on the counter, then yes, counter can work if you fix 30 nanosecond period. So clock period is 30 nanosecond, then the frequency is 1 by 30 nanosecond. You know that, correct? So this is the answer. So if I simplify it, nano means 10 power minus 9. So it would be 1 by 30 into 10 power minus 9 if it goes up, 10 power 9. So 10 power 9, hedge, right? Right. So 1 by second is hedge. 10 power 9 by 30 is, if you simplify, it would be 1 by 3 of 10 power 8. Okay, whatever. So just remember it. 0.33 into 10 power 8 hertz. All right. Okay. Now, but what about this output? That is one more interesting question. Correct? Okay. So this output also, if you consider, okay, in the question it is not mentioned. He was talking about only like the counter, correct? But if that output is also considered, then that requires 10 more nanosecond, right? So finally that delay should be 40 nanosecond. So if you consider this gate also, this AND gate also, then the answer is 40 nanosecond. That means if you keep 40 nanosecond delay, then that would be super fine for this machine to work properly. Okay, every J and K inputs will take the input properly, correct? And also we can get the output properly.